4C operations with vectors, mathematical techniques. Graphical vector addition using sketches provides quick, convenient results, but lacks precision and accuracy. Even carefully drawn vector diagrams are subject to drawing errors. For physics, mathematical techniques involving trigonometry allow you to perform vector addition with much greater accuracy. 4.7. Solving triangles. In solving two-dimensional vectors, you will have to solve for unknown quantities in vector triangles using the mathematical tools taught in algebra and geometry. To help you find the measure of angles and lengths of sides in triangles, you must know the rudiments of trigonometry. We will review some of the more important trigonometric concepts here. One useful principle of trigonometry is that two triangles are similar triangles when the three angles of one triangle equal the corresponding three angles of the other triangle. The angles, not the sides, determine similarity. Compare the triangles in Figure 419, which have different side lengths, but equal corresponding angles. Upon closer inspection, you should see that the lengths of the sides are indeed related, the ratios between corresponding sides of triangles. A and B are all the same. In fact, all similar triangles have proportional sides. Physicists and mathematicians use this important relationship to solve vector triangle problems. By far, the most common triangle found in physics problems is the right triangle, which has one 90-degree angle. Right triangles possess several properties that make it easy to determine unknown sides and angles. Study Figure 4-20 carefully before you proceed further. The two acute angles, which are less than 90 degrees are labeled A and B. The measure of angle A is, and the measure of angle B is beta. Side alpha is opposite acute angle A, while side B is opposite acute angle B. The hypotenuse, the line segment opposite the right angle C, is labeled C. Because the sum of the interior angles of a triangle is always 180 degrees, you can determine an unknown acute angle in a right triangle if you know the measure of the other acute angle. Similarly, if you know two of the sides of a right triangle, you can find the third according to the Pythagorean theorem. A square plus b square narrowing c square. A significant benefit of using a right triangle is that one of the angles is always known the right angle. As long as either two sides or an acute angle and a side are known, all the angles and all the sides in a right triangle can be determined mathematically. This can be accomplished by taking advantage of the proportionality of similar triangles. The values of ratios of corresponding sides in similar triangles are always the same. The ratios of the hypotenuse or sides that are either adjacent or opposite to a specified angle are given special names. The sine of an acute angle is the ratio of the opposite side's length to the length of the hypotenuse. From Figure 420, you can identify the sines of angles, alpha and beta, which are written sine alpha and sine beta. Sine alpha, chamchan, opposite over hypotenuse, chars A over C. Sin beta, chanch, opposite over hypotenuse, charpchan B over C. Similarly, the cosine of an angle is the ratio of the length of the angle's adjacent side to the length of the hypotenuse. The cosine of A is written cos alpha. Cos alpha, noshn, adjacent over hypotenuse, ha B over C. Cos beta, and adjacent over hypotenuse, A over C. The tangent of an acute angle is the ratio of the length of the side opposite the angle to the length of its adjacent side. The tangent of alpha is written tangent alpha. Tangent alpha, shashan, opposite over adjacent, A over B. Tangent beta, crash, opposite over adjacent, crash B over A. The values of sine, cosine, and tangent for any angle are easily calculated using a scientific calculator. Given only the sides of a right triangle, how can you find the measure of the two unknown acute angles? You could draw a scale model and measure the angles with a protractor, but this technique is not precise. Instead, it is better to use one of your calculator's inverse trigonometric functions, usually shown as a secondary function to the corresponding trig ratio, keys, arc sine, arc cosine, and arc tangent. The argument for these operators is the ratio of the appropriate sides, and the output is the corresponding angle in the definition of the function. Given the right triangle in Figure 422, Suppose you want to find the measure of the angle whose opposite side is 7 units and whose adjacent side is 8 units. Tangent alpha, Chapter opposite over adjacent, for 7 over 8, for 0.8750. Using the inverse tangent function on your calculator gives you it directly. Alpha arctan, 7 over 8. Alpha about 41.2 degree. The inverse tangent equation above may be read, alpha is the angle whose tangent is 0.8750. The exponent 1 in an inverse trigonometric operator does not invert the expression. 4.8 Vector components. Before we look at the mathematical methods for adding and subtracting vectors, we first need to develop the concept of component vectors. Every vector lying in a plane is the resultant of the sum of two special vectors, called component vectors, or components. To understand the relationship of components to the original vector, imagine two flashlights shining on a vector as in Figure 423. Note that the light beams are parallel to the vertical and horizontal axes of the vector's coordinate system. The shadows of the vector cast by the flashlights are projected onto each axis. These shadows represent the component vectors. In fact, components are often called projections of the vector onto the coordinate axis. Components are parallel to the coordinate axis and are therefore perpendicular to each other. Mathematically adding vectors involves combining their x components and their y components to obtain the components of the resultant vector. Quickly finding the components of a vector is therefore very important. This is where trigonometry comes into the picture. When a vector and its components are sketched together in a triangle, they form a vector triangle. The vector triangle for any given vector is a right triangle because the component vectors that form the legs, shorter sides, of the triangle are perpendicular to each other. As long as the vector's length and angular direction are known, you can find its components using trigonometry. Vector components are labeled with the original vector's symbol and include a subscript of the axis to which the component is parallel. For example, the x component of the displacement vector d is dx. The angle used when determining a vector's components is usually the acute angle between the vector and its horizontal coordinate axis, the axis parallel to the horizontal component. We will call this the reference angle, alpha. The reference angle may or may not be the same as the vector angle, theta, depending on the reference direction used for the problem. Regardless of the orientation of the original vector, the reference angle is always a positive acute angle within the vector triangle. When the reference angles for several vectors are required in a problem, you should label each angle with its vector name as a subscript, e.g., alpha A, alpha B. The scalar values of the component vectors are called scalar components. While the magnitude of a component vector is always a positive, the scalar value may be positive, negative, or 0, depending on the orientation of the original vector. The sign indicates the direction of the component relative to its coordinate axis. Positive scalar components point up and to the right. Negative scalar components point down and to the left. Note that the one-dimensional vectors discussed in Chapter 3 had only one component, the vector itself. When the component vectors of a given vector have been identified, we say that the vector has been resolved into its components. Completing the following steps will help you resolve vectors. Select a convenient coordinate system. Usually, the coordinate axes will be vertical and horizontal, but other orientations are possible depending on the situation. See Figure 424. Note the kind of directional system used, Cartesian or map. Determine the reference angle, alpha, for the vector. Identify this angle and determine its magnitude from the geometry of the problem. Find the magnitude of the horizontal scalar component, phi x, 5 as alpha, where v is the magnitude of the vector v. Find the magnitude of the vertical scalar component, vy, v sin alpha. Assign the correct signs to the scalar components based on their orientations to the coordinate axes, the positive reference directions in. The Cartesian system are the positive x and y axes. In the map system, north and east are positive. Always refer to the problem sketch when assigning scalar component signs. Vectors described using a map system of directions are resolved in the same way as vectors in a Cartesian coordinate system. The cardinal map directions must first be redefined as Cartesian axes. The east-west line becomes the x-axis, and the north-south line the y-axis. Resolve the vectors as usual. Components may be labeled VNS and VEWW to indicate that they are map vector components. Component vectors may be summed to find the original vectors. This may seem to be an obvious statement, but you will need this skill to determine resultant vectors. First, let us look at a graphical example. Three-dimensional vectors can be resolved into three components. In this case, the components are parallel to the x, y, and z axes. By convention, the x and y axes lie in the horizontal plane, and the z-axis is vertical. The following example shows how we obtain a three-dimensional vector from its components. 4.9 Operations with components. Components enable you to add or subtract vectors with great precision. Instead of using a protractor and a ruler, you use a calculator. Let's look at an example that allows us to put this tool to use. Example 4.9 covers every step required for mathematically adding two vectors. Notice that you must convert vectors to scalar components in order to perform algebraic or trigonometric operations on them. At each step, your solutions should show the calculations and the values of the variables. Because vectors can describe displacements, velocities, accelerations, or forces, they can have a variety of different units. When you add or subtract two vectors, make sure that they have the same units. 4.10. Using vectors to solve problems. One of the most difficult problems with forecasting hurricane landfall is predicting the track of the storm. This uncertainty creates huge logistical problems for large areas threatened by the storm. People must be evacuated, buildings must be protected against damage, and disaster preparedness measures must be initiated. How can meteorologists use vectors to improve hurricane track forecasting? For many years, images from U.S. weather satellites have been used to observe the motions of hurricanes. The motion vector for the eye of the storm was used to predict the storm's track for a few hours after each photo was taken. But this information was not useful for long-term predictions. Analysts superimposed wind data, which was recorded by aircraft that flew through the hurricane itself, onto the satellite photos to better understand the storm's motions. But the data often arrived hours too late and had limited predictive usefulness. In the 1990s, improvements in image processing algorithms allowed meteorologists to obtain motion vectors of all visible parts of the storm directly from satellite images. These atmospheric motion vectors, AMV, provide a much more comprehensive view of the storm motions in nearly real time. The next problem to solve involved using the AMV data in the storm track prediction computer models. Since Hurricane Katrina, which devastated a large region in the southern United States in 2005, National Weather Service meteorologists have been experimenting with rapid data scans of satellite storm images, as frequently as 3 to 7 minutes apart, to acquire AMV data for numerical models of storm prediction. These computer models evaluate thousands of motion vectors and then calculate what forces must have been exerted on and by the storm in order to produce those vectors. The output of the models is a prediction of the direction and speed, another vector, that the storm will likely exhibit over a period of 24 to 120 hours. The rapid scan and experimental results have been very encouraging. As the accuracy of future hurricane track forecasts increases, evacuation efforts will begin earlier and become more effective. By better preparing for natural emergencies like hurricanes, we improve our ability to save human lives.